Still a Sunday evening for me, but it's a good Monday morning to you all. I hope you're all nice and warm there. It is minus 13 Celsius outside here right now, and lots of snow. So with that, thanks for your interest in this technology. Um, Fluidized bed hydrodynamics. We're going to go through the entire technology in the next few days, but today I'm going to focus on the most fundamental aspect of the fluidized bed technology, which starts with the process of fluidization. Fluidization or fluidized beds are just contact devices. In chemical engineering technology, terminology, we can call them reactors, but basically it is a device where different phases come together. Uh, Before I show you a little bit of historical development, I should also mention that it is very common that we call a gas solid two phase or gas liquid or liquid solid two phase. They are not the same phase of the same substance. So we should not mix those with, for example, water in a boiling heat transfer. Water could be both in liquid phase and gaseous phase, which forms a two-phase system. This is different. This is gas and solid, two different substances, but together we call it two-phase. So when did it all start? It started in 1900s. In Germany, named a person called Winkler came up with a gasifier, and then obtained the first patent called the Winkler patent in this field, basically where solid and gas came together to form a gaseous substance. Then chemical refineries started using it for fluid catalytic cracking in early 40s, which probably it was at the same time as the World War II. And from there on, industries got a hold of it and it started using a bubbling fluidized beds for mainly, again, as contact devices and as combustors. Then interesting things happened. And many of you may not probably won't remember. In the 1980s, there was a big oil crisis called the Gulf oil crisis. That oil crisis gave a lot of importance to solid fuels, mainly coal. Coal became very, very important and basically for energy generation. And then fluidized beds became incredibly attractive for the reasons that we're going to cover. Then was the beginning of the circulating fluidized bed combustion era. I should just pause a second and tell you that in the late 80s, that was my first introduction to India, where I was part of a team trying to helping Indian Electric Authority to replace their pulverized coal-fired boilers to circulating fluidized bed boilers. Then I spent a little bit of time at IIT in Kharagpur lecturing about this technology. So moving forward, today,
Professor Feridun,
yes,
uh, just sorry to interrupt you. Can you please open your the presentation in the full screen mode?
full screen. Am I not
Yeah,
in
yeah,
full screen?
yeah.
Help me how to do this.
Yeah, in the left corner, there is an option in the left bottom.
Yes,
Sorry, right bottom corner. Yeah, yeah, yeah. It's there. Yeah, this one only. Yep.
that's it.
Yeah, thank you, thank you.
Okay. So again, this gives you a little bit of historical context, starting in the 40s and today where we are in the fluidized bed technology. So, what is a gas solid two-phase flow system? It is where, as I mentioned, gas and solid, they are together in a confined space where gas is in motion and is trying to disturb the solid particles in one way or another, and trying to create an environment where solids will move away from a stagnant state and act like a fluid. So when this happens, we start with a fixed bed. We use fluidized beds. When it's really, really fast, it becomes we pneumatically transport those particles, or we use them in catalytic reactors. So as you will see, let me just show you here on the application side. I don't know if you can see my cursor here. So we use it, we burn fuel, or we gasify fuel. We use it in petrochemical processes like catalytic cracking, or waste treatment, or carbon dioxide capture in many different applications. So those applications all the time. They are um, reactive most of the time applications that involve heat transfer and mass transfer. For those to be maximized and to be in a very advantageous position for the user, you have to have the hydrodynamics of the system you're going to design perfectly figured out. You have to understand the hydrodynamics. That's why it is very important to understand basic principles of hydrodynamics of these kind of systems, predominantly fluidized systems, so that we can successfully design heat transfer surfaces or predict heat transfer and mass transfer, which are the fundamental outcomes of what we're trying to do. So, what are the challenges in designing, understanding hydrodynamics? It is very complex. We have a random motion of thousands of particles, and they are behaving in a way that is not very easy to predict by standard simulation methods. The behavior is nonlinear because it moves in various directions because of the size of the reactor and also the size of the particles. And most importantly, a lot of the fundamental research in this area has started in labs. So the one of the biggest challenges is how do you move this successfully from a lab scale application to industrial scale application without compromising the performance of your reactor. So for that, we need to understand fully how both phases, gas and solid, they behave in such environment for a given application. So this is a very schematic of how fluidization happens. Think of a vessel and fill this vessel with solid particles. I'm sure you've seen it in your some of the demonstrations or in labs, and start passing gas through it. And this is just these represent stars represent solid particles, spheres, or these are various size bubbles, and they move upward. This is a bit misleading here. These bubbles do not stay as bubbles. Of course, at the surface of this, they will erupt and project particles into this zone. But nevertheless, This is the idea of fluidization, that particles will be suspended. Just shortly, I will show you in what stages this happened. So, as I mentioned, this, by fluidizing a solid bed, you enable it to have a much more higher heat transfer coefficient, heat transfer rates, and mass transfer because of higher levels of degrees of mixing taking place in here. So it's like a very good mixer that enables you to do that. As I said, it behaves like a fluid. So when you tip the vessel here, you will see that the surface reacts to it. If you put a light object into it, it will float. So if you put a little ping pong ball in there, it will float as if it is suspended in air or liquid. Uh, if you put a little hole here, it will gush out. So it will obey the law, Archimedes law, or higher laws of hydrostatic pressure, and it will obey all the hydrostatic laws as if it is fluid. Whereas here you have a suspension of solid and gas. So to get there, we need to go through various flow regimes. So again, let's go back to the example I gave you. We have this vessel, let's say it's cylindrical, and we fill it to a certain level with solid particles. Let's say sand particles, okay? Sand particles, let's make it up, of 200 micrometers, okay? And they're nicely sitting there. And we start blowing air from under, okay? And I have something here that we will call it later on a distributor plate that has holes enabling the air to pass through, but preventing these solid particles from raining downwards, okay? So gas starts going, nothing is happening. At one point, you will see it like, oh, it started boiling and then it expands, okay? Think of it like you're boiling a pot of water, okay? You turn the heat on, we wait, and then as the temperature of the water increases, it will level and boiling starts. So similar to that, so you have this homogeneous expansion only when you have very fine powders. But regardless of that, when the gas velocity, and this is in the direction of increasing the gas velocity. When the gas velocity increases to a level, you start seeing bubbles. So understand this. Air is flowing through this, nothing is happening. The moment it starts expanding, air that is in the excess amount that is required to suspend this starts going through the bed in the form of bubbles. We call this the incipient, the onset of fluidization, bubbling fluidization. Okay, if the vessel is too narrow, I will explain it later. Bubbles coalesce and they become one, and slugging, this is a behavior we want to avoid. So moving from bubbling to this, we're further increasing the gas velocity. We reach a turbulent state. Turbulent state is the turbulence of, it's not the turbulence of air or gas, it's the turbulent motion of the particles. Particles now start going all over, and it is behaving as if they are small eddies. Of course, the scale of the eddy is determined by the size, diameter of the particle. Then you further increase it, these bubbles, they disappear and fast fluidization will start, and you will see clusters of particles. And then if you go further, you will enter into pneumatic transport, that you will see no bubbles, nothing, and the particles are all moving. They're transported upward and in any which direction. Okay, so I think, yeah, I covered these. You will have it, your slides. Again, this is a very famous diagram by somebody who is one of the fathers of fluidization, Professor John Grace, late Professor John Grace, and he is, this is again another very clear illustration of how we go from fixed bed to a bubbling regime to slugging, turbulent, fast, and pneumatic. So I wanted to show this again because in the next hour, we're also going to talk about a different kind of fluidized bed, which will involve liquid, for example, water and solid particles. So you will see that in the fixed bed, we can use both gas and liquid at low velocities, and you'll maintain a fixed bed. It's like you have upward moving coffee percolator. At the minimum fluidization, again, you can use gas or fluid. As you can see, the bed expansion that takes place at minimum fluidization. But if you want to have this incipient smooth fluidization, this is only possible if you have liquid as the transport medium. Okay. And bubbling, we explained this with gas, slugging, gas. So lean phase fluidization with pneumatic transport will happen. Again, we can use both gas and liquid will also help transport particles. So those are the 1, 2, 3 cases. Gas or liquid could be the medium, but in any other case, it is gas only. So what are the key parameters in start thinking about these kind of vessels? So we need to understand the superficial gas velocity of. And the superficial, why do we call it superficial gas velocity? Um, it is if you had the vessel just empty with nothing in it, and then pass the air through it, volume of air, divide volume by a volumetric rate to the cross-sectional area, you'll have the velocity. Superficial velocity is the velocity that takes the solid mass or volume into consideration as well. So we need to understand how much air we will need for a given application, for a vessel of given size, and particles of given diameter. So for that, we need to know the particle properties. For example, how do you define the particle size? I don't have time to go through the entire thing because it will have taken many, many hours. But um, obviously, particles will not be all of uniform spherical shape. They could be of different shapes. Therefore, the particle size we use is average particle size taken into the shape factor and everything else into consideration. But nevertheless, we need that particle diameter for the calculation of drag force and Reynolds number and any other parameters. So it's a very important parameter to have it on site to determine. So continuing on, thanks for the warning. I don't know how I got muted. We need to define a Reynolds number because it will help us understand the flow regime in which we want to be in. And in this case, please remember Reynolds number we're talking about. I am assuming you know what Reynolds number is. Okay, its definition is given here. And writing Reynolds number, we always use a characteristic length. If we are defining Reynolds number in a pipe flow, it's the diameter of the pipe, but in this case, Reynolds number here is the diameter or average diameter of the particle. But all other properties, density of gas, superficial gas velocity, and viscosity, they are all gases, of course. So we need to find the minimum fluidization velocity. There is no given formula. They're all predictions or correlations, but nevertheless, for a given geometry, given application, given vessel size, given particle size and characteristics, we need to figure out what a minimum fluidization velocity will be. So you will see you can determine your blower or fan size, which is very important. If you don't have the right blower, then you cannot fluidize the bed. So minimum fluidization velocity is the velocity. Let me go one ahead and then I'll come back to this one. When you have a packed bed, that means it is not fluidized. This is your particles. The gravitational force of this particle, okay, is higher than, or drag force is smaller than the gravitational force. So gravity is still pulling it down and holding it down, okay? You can see me okay too. Here is our particle, okay? This is a tennis ball I'm holding. If I let it go, the gravity force will make it fall, okay? In a packed bed, it is standing like this. Air is going through it, around it, but gravitational force is still larger than the drag force holding it. So in a fluidized state, this is almost the same. The drag force is equal and slightly higher than the gravitational force, therefore puts this in a suspended state, which we call the fluidized state. This is the onset of fluidization. So to put this in a formulaic way, weight of solid particles, we subtract the buoyancy acting on particles. Of course, if it's air, this buoyancy effect is negligible, but if it's water or liquid, of course, it is appreciable, therefore you have to take it into consideration. Then this will be equal to pressure drop of fluid across the bed, okay? How much pressure, that pressure was when air pressure was when it entered the bed, and what it is leaving the bed, and this is the pressure drop, and you multiply it by the cross-sectional area. That will give you the equation that is required to calculate a minimum fluidization velocity. Of course, theoretically, you can't do this, but there are various correlations, dozens of them. The most reliable ones, they're all derivatives of Ergun's equation. For small particles, where Archimedes number determines what that small is, this is the correlation that it gives you the minimum fluidization velocity. For large particles, this is it. So particles that fall into, and I'm going to show you in a minute, in Geldar's classification as small particles, you can calculate it this way. Large particles, again, in Geldar's classification, we can calculate the minimum fluidization this way. So this is a very important graph. This is experimental verification of a theoretical pressure drop air velocity curve, okay? And I'm going to walk you through this. When we are in fixed bed, as you increase the air velocity, it will be, just calculate the pressure drop through drag force. You will see this linear increase in the pressure drop. The more air you put through it, higher will be the pressure drop through it. Up to a point. You see this point here I'm circling? This is where the fluidization starts. So these were like this until fluidization start. When fluidization starts, they become like this. Okay, after which, no matter how much air you put through this, pressure drop remains the same just because they're suspended. The gravity force is overcome already. Therefore, until you start blowing air so high that you're losing these particles, okay? They're no longer in suspension, and this will remain the same. So a quick question to you. Think about this for a second. I will go back. Now I'll start reducing the air. I'm moving in the reverse direction, but instead of following this curve, I am following this one. I'm sorry, I went up this way, the dotted line. Coming back, I'm coming through the solid line. Why is this? It's the same air, the amount of air, same velocity, same vessel size, everything. It's because when trying to fluidize, you have to break the contact force also, in addition to gravity, contact force between these two. When it's slowing down, you don't need that extra resistance until they touch each other. This will be, when we are talking about drying, a very important factor because these particles will be wet particles and it will be much more difficult to break them apart. We need to define the bulk density of this bed. And how do we do this? Uh, Simply, the mass and divide it by volume, and this will give us the bed voidage, and the bulk density is defined as mass and volume relationship. So these are all preparation for you to understand all the parameters that are involved in a very complex and difficult hydrodynamic environment to model or to design. So far we've covered a number of things. We understand now how fluidization happens. What are the physical processes or physical environment that it happens? Why it happens, and when it happens, what is the stage that we call? It's called the physical fluidized stage, at which time you have solid particles, you have gas around those particles, plus you have gas in the form of bubbles, okay? You actually have solid particles, you have gas flow, incipient gas flow, and you have anything that is in addition to that is present in the form of bubbles. Why do we prefer, again, fluidized beds, especially for thermal processing over conventional ones? As users, as engineers, you should know that uh, anything that behaves like fluid, you can handle it a lot easier. So it's for the ease of handling. You should know that if you want a high performance from any reactor, you have to have a rapid mixing in that reactor, and that provides us. Circulation is a lot easier when it's in liquid fluid state. Um, you can easily use this for large operations. Again, as I mentioned, uh, you have high heat and mass transfer. Therefore, if those are higher than the conventional ones, to obtain the same rate of heat transfer, you will need to use a smaller heat transfer surfaces. Again, what do we use them for? For combustion power generation or gasification power generation in the food industry, because it is a contact physical environment. In chemical industries, from FCC to other pharmaceuticals, mineral processing, and everything. One interesting, very interesting application of fluidized beds. Uh, it actually, you can use it as a bed. It is used in hospitals for burnt patients. If a patient is burned, it is very painful for the patient to be touching the bed or to even have sheets, anything on them. So a fluidized bed fluidizes, suspends the patient. Therefore, you can easily turn the patient around and maneuver. So just one application. So several different areas that you can think of. To summarize, there are four um, um, different concept phenomena that you have to consider. If it's reacting, you have to understand the kinetics of that reaction. Mass transfer, you need to be able to predict from the particle Reynolds number, heat transfer again from Nusselt number and gas Reynolds number, and fluid dynamics will be determined by all the factors that I summarized. Quickly, I'm just giving you examples. They are very messy, complicated. They're, as you can see, there are lots of constants indicating that they are derived from a large number of experiments, but within certain experimental parameters. Here you can predict the packed bed pressure drop. And then if the particles are moving, then you can calculate the void fraction and therefore the pressure drop accordingly. Okay, just uh, telling you this. If the bed is at fluidized conditions, then its void fraction is high. Solid content is low, therefore, surface area of reaction is low, surface area, pressure drop is low, good heat transfer, good mass transfer, they're all possible. I mentioned about slugging, something that needs to be avoided. So it is determined by particle size compared to the reactor or vessel size and how much gas you're using. And especially if you are using large group D particles, you will end up having a slug here. All bubbles will coalesce, will form a big one, and then this will cover here. Therefore, you lose all the advantages of heat mass transfer advantages of a fluid bed. One other concept when you're designing is to predict the transport disengagement height. What is transport disengagement height? It is a non-physical height. If you follow this graph, okay, solid volume fraction is increases as you go here. It changes from denser to leaner, and then this region is called the freeboard. That when the bubbles erupt here, particles are projected in here, and this is where you no longer have a dense bed, and you have the freeboard. So this height is important. If you're designing a vessel, the higher this reactor is, the more expensive it will be because you have to build more material, you have to add all kinds of things. To predict the right transport disengagement height, which means that beyond this height, nothing is happening. Okay, at which larger particles return to bed while smaller ones become entrained. Therefore, you no longer have any reactions here. Okay, so this is the best prediction so far that transport disengagement height should be 12 times the bubble diameter, diameter of the bubbles erupting at the bed surface. So again, a good design parameter for you to have. So let me go back here. Underneath, as I said, the gas comes, the particles are supported physically, and then air is allowed to pass through here. To do that, you have to have a plate or a device that will prevent particles from going down into the plenum, but will allow gas to go upward to go through this with a minimum pressure drop possible. So we call this a distributor plate, if it's a plate, or it could be nozzles, a distributor nozzles, okay? Uh, again, a rule of thumb for the design of this, a minimum pressure drop of such a device will have to be 10 to 30%, not more than 10 to 30% of the bed pressure drop when you're designing this. There are so many very complex, different distributor plate designs. It will be a completely another topic, but you will know that this is the basic principle of it. The other one is this distributor plate is called the perforated plate. Basically, think of so if you have a plate, let's say you're using particles, as I said, 200 micron. So your hole size will have to be smaller than 200 micron. And the smaller the hole size, the larger the pressure drop. So you need to optimize the hole size. And also, of course, if it's too large, you will lose the good mixing characteristics. So what you do, you use two plates and they are eccentric. Therefore, if a particle falls through one hole, it won't go through the second plate. It will be stuck there and then it will be pushed back upward. Nevertheless, we call this a plate. These are bubble caps, which are in this fashion. The air goes through cylinder this tube, and then it's impacted and comes out through this analyst and is able to, as it comes out, fluidize the particles. Okay, it is of course more effective, but also more expensive and also causes higher pressure. Now, this is a different term. We call it elytration. That means this is when you start the particles after the transport disengagement height, lighter particles, they no longer stay in bed. They escape, and to do that, of course, your velocity of the gas will have to be higher than the particle terminal velocity, and this is how you calculate the terminal velocity of the particles. And if your gas velocity is higher than this, and then you will lose all these particles. And if you want to gain these particles, you will add a cyclone at the end of your bed to capture those particles that escape from bed and then bring it back into the bed, which will quickly tell us what to do as a next step. So, as I said, I tried to simplify it as best as I could, but to get the fluid dynamics correct is the most essential part for successful mass transfer and heat transfer operations in the fluidized bed. Speaking of heat transfer, again, a lot of correlations are used to predict that. Why? Here is a schematic of in a bubbling fluidized bed, okay, the complexity of the case. So you have bubbles, as I said, and you have incipient air, and this is, let's say this is a combustor. So you have reactant flow, bubbles, they contain hot gases, they contain unburned fuel, they contain gaseous fuel, they contain all kinds of things. And you have particles, particles touching the heat transfer surface. So you have three mediums. You have hot air, you have bubbles, and you have single particles or clusteral particles, all touching this heat transfer surface. When I say heat transfer surface, it's like a tube, right? Water is going to go from here, exit from here, capture the heat from all of these, therefore will become hot water or steam for whatever operation we're going to use it. So this is particle convection, gas convection, radiation, all of those, they come into effect. And if we have a surface here, like a wall, a refractory wall, you have particles touching this wall. So I hope I'm making sense here. So this is my particle. This is now very hot. If it's a combustion process, the bed is at around 800 Celsius, okay? And I want to extract that heat. So this is my wall. It's gonna touch. As it touches, it will transfer heat. Heat will be transferred from this hot particle to the cold surface. And if it's just one particle, see here how much of its surface is in contact with the wall. So it is very difficult to properly model this, and especially if you have a cluster of particles touching here one by one. And this isn't a bubbling operation. So this is just to show you some models and again, how to predict heat transfer coefficient through Nusselt number. Mass transfer again is similar through short number. You can use various correlations, but may understanding that for those, again, gas flow is important. When you have, turbulent flow in in an environment where there are no solid particles, even with that environment, it is, except in numerical methods now, difficult to model a turbulent flow, the scale of which and how, mixing and everything. But when you have particles or cluster of particles, they are influenced by the turbulence of the flow, but they also modulate the turbulence. So that means it's like they cut down the scale of turbulence. So there is no known correlation that will give you exactly what they'll be. So everything that I'm showing you here, they are predictions, such as this one.